Before we look at partial derivatives, let's do a quick review of the role of a constant in a derivative. And we'll look at this function as an example, y equals 7x to the fourth plus 8. Now you'll notice the constants in this function are the 7 and the 8. The 7 is the coefficient of the variable term x to the fourth, and the 8 is a constant term, a term that has no variable in it. When we take the derivative of this function with respect to x, we look at the first term as a constant times the function x to the fourth. So the derivative of the first term is that constant 7 times the derivative of x to the fourth, which is 4x to the third. The second term, the 8, is just a constant term without a variable, and we know that the derivative of a constant term is 0. Now those ideas are going to be very important when we start to look at partial derivatives. So keep in mind we have to be able to identify what the constant is in our function before we take the derivative of that function. So let's look at a definition of what a partial derivative is. If we have a function that contains two or more independent variables, a partial derivative is a derivative in which one of the independent variables is allowed to vary, and the other independent variables are held constant. In other words, we will consider one of the variables to truly be a variable, and all of the other variables to be considered constants. Now here's an example of a function which contains two independent variables, x and y. If we want to take the partial derivative of this function z with respect to x, this is the notation we can use to describe that. Now what's going on with a partial derivative with respect to x is that we're considering the x to be the variable. Everything else is a constant. So the 4 is a constant multiplying the x, and 3y is a constant. So what's the partial derivative of that? Well, the derivative of 4x is 4, but the derivative of 3y is 0 because 3y is considered a constant, and the derivative of a constant is 0. So the partial derivative of z with respect to x is equal to 4. How about the partial derivative of z with respect to y? Well, now we're considering y to be a variable. Everything else is a constant. So when we take the derivative of 4x, we're really taking the derivative of a constant, which is 0. And the derivative of 3y is 3. So the partial derivative of z with respect to y is equal to 3. The trickiest thing about partial derivatives is that you're going to have to consider part of your function to be a constant even though it looks like a variable to you. Now let's look at this function, w. It has three independent variables, x, y, and z. And we're going to find some partial derivatives of w in the first case with respect to x. Now that means that everywhere we see the variable x, we'll look at the x as being a variable. But anything else that's not an x on the right side of this equation we'll consider to be a constant. Now to help us out, let's color code things. On the right side, you see that all of our x's are still colored in black. But anything that's not an x, we're coloring in red, meaning those terms, those parts of those terms, are considered constants. So let's take this term by term. The derivative of x squared is still 2x. But the derivative of minus xy is minus y. That's because the y is considered to be a constant. And those last four terms are all constant terms. So the derivatives of each of the last four terms is 0. So our partial derivative is 2x minus y. Now what if we want the partial derivative of w with respect to y? Well, that means that the y is considered to be a variable, but anything else that's not a y is a constant. So now everything that you see in red we're going to consider to be a constant. The derivative of the first term, x squared, and the last two terms, 2z squared and z, all those derivatives are going to be 0 because those are just constant terms. The derivative of the second term, minus xy, is minus x. The derivative of y squared is 2y. And the derivative of 2yz is 2z. That's because the 2 and the z are both considered constants. And finally, the partial derivative of w with respect to z. Now we'll look at everything that is not a z on the right side of the equation as being a constant, which means when we take the derivative of the first three terms, we're taking a derivative of a constant, which means those derivatives are all 0. But the fourth term, 2yz, has a derivative of 2y. The fifth term, 2z squared, has a derivative of 4z, and the last term, z, has a derivative of 1. Let's try this one. So now our function is written as f of xy. It's a function with two independent variables, x and y. And you'll notice that we're using slightly different notation this time. F sub x means the partial derivative with respect to x, and f sub y is the partial derivative of f with respect to y. So for the partial derivative with respect to x, anything that's not an x is considered a constant. So once again, we've color-coded things. The 3 and the y in the first term are considered constants, and the y in the second term is considered a constant. So the derivative of the first term is 3y, our constant, times the derivative of x squared, which is 2x, or just 6xy. And the derivative of xy is y. And the partial derivative with respect to y, well, we'll have to consider anything that's not a y to be a constant. So the derivative of 3x squared y is just that constant 3x squared, and the derivative of xy is just the constant x. Here's a function f, which also has two independent variables, x and y, and we want to find the partial derivatives with respect to x and then with respect to y. For the partial derivative with respect to x, anything that's not an x we'll look at as a constant. So we'll take the derivative of the first term, e to the xy. That would give us the e to the xy back again, times the derivative of the exponent, which is y. And the derivative of the second term, well, since y is a constant, we'll have that constant times the derivative of the natural log of x, which is 1 over x. We could decide that we want to rewrite that. For the partial derivative with respect to y, we'll have to look at everything in our function that's not a y as being a constant. So to take the derivative of the first term, we'll get the e to the xy back again, times the derivative of xy, which is x. Remember, x is a constant. Now the second term is a little bit trickier. We want to take the partial derivative of y times the natural log of x. But since x is a constant, the natural log of x is a constant. So the derivative of y times the natural log of x is just the natural log of x. Now we've looked at second derivatives before. We saw that they were derivatives of derivatives. We also have second order partial derivatives, which are partial derivatives of partial derivatives. Now there's lots of notation for second order partial derivatives, and there are 4 different second order partial derivatives. All of these notations mean that we're going to be taking a partial derivative with respect to x, and then we'll be taking a partial derivative with respect to x of that again. This notation would mean that we're taking a partial derivative with respect to x, and then we'll take a partial derivative of that with respect to y. All of these notations mean that we're taking a partial derivative with respect to y, and then taking a partial derivative of that derivative with respect to x. And finally, we could take a partial derivative with respect to y, and then take a derivative of that partial derivative with respect to y again. So let's take a look at this problem. For z, which is a function of variables x and y, we want to find all four of our second-order partial derivatives. So let's start by looking at the partial derivative with respect to x. Now that means that anything that does not look like an x we're going to treat like a constant. So the derivative of x squared is 2x times that constant y to the third. The derivative of x to the fourth is 4x to the third times the constant y. And the derivative of x is 1 times our constant e to the y. So that's our first partial derivative with respect to x. Now we'll use that partial derivative with respect to x to get the first of our second-order partial derivatives, f sub xx. That means look at f sub x and take its partial derivative with respect to x. So that means everywhere we see a y, the y will be considered a constant. So the derivative of 2xy to the third is 2y to the third. The partial derivative of 4x to the third y is 12x squared y. And the derivative of e to the y is just 0 because e to the y would be a constant. Now we'll still look back at our first partial derivative, f sub x, to get the second partial derivative, f sub xy. Now we're going to consider y to be our variable and x to be our constant. So the derivative of 2x y to the third is 2x times the derivative of y to the third, which is 2x times 3y squared, or 6xy squared. The derivative of 4x to the third y is just 4x to the third. And the derivative of e to the y is e to the y. So we have two of our second-order partial derivatives. To get the other two, we'll have to take a partial derivative of our function f with respect to y. So back up to the top. In our first term, x squared y to the third, x squared is considered a constant times the derivative of y to the third, which is 3y squared. In the second term, x to the fourth y, x to the fourth is a constant times the derivative of y, so that's just x to the fourth. And in the third term, x is considered a constant times the derivative of e to the y, which is e to the y. So derivative of x e to the y is still x e to the y. Now to get the partial derivative of that with respect to x, we'll look at f sub y, and we'll consider the x to be a variable and the y to be a constant. So the derivative of x squared is 2x times our constant 3y squared, so that's 6xy squared. The derivative of x to the fourth with respect to x is 4x to the third. And the derivative of our third term, x e to the y, since x is our variable and e to the y is our constant, is just our constant, e to the y. And for the last of our second-order partial derivatives, we'll look at f sub y, but now we'll take the partial derivative of that with respect to y. So for the first term, 3x squared y squared is our variable. The derivative of y squared is 2y times our 3x squared is 6x squared y. The derivative of x to the fourth is 0 because x to the fourth is a constant. And the derivative of x e to the y is x e to the y. X is a constant, and the derivative of e to the y is e to the y. So those are the 4 second-order partial derivatives. You'll notice that to get each of them, we have to do a first-order partial derivative first. So as you can see, the trickiest part to working with partial derivatives is keeping in mind what part of your function is considered to be a variable and what part is considered to be a constant.